Now, in the continuation of virtual memory, demand paging, and page fault, let's see the page replacement policies or page replacement algorithm. Now, whenever there is a page fault occur into the main memory for any of the pages, it will call the virtual memory manager of the operating system. This virtual memory manager will take the page fault as a trap or as a interrupt and block all the running process and contact to the disk manager, which is a file system. And from the file system, the device driver will be called, and the device driver will call the device controller or give the control to the device controller, which is a hardware, specific hardware to the secondary memory. This secondary from the this secondary memory, the page will be located and swap into the main memory, and the page table will be updated. The whole process is taking by the virtual memory manager, which will do all those processes, and this whole time taken by the page fault is called page fault service time. Now, as we have discussed, so whenever there is a memory and the memory is full and we want to replace some of the page from the memory and we want to put the new page into the memory, so for that we use the page replacement policies. And this page replacement policies uses reference string. What it will use? It will use reference string. What is do you mean by reference string? So reference string is a set of successively unique page referred in the given list of virtual address or physical address. So the physical address or virtual address generated by the CPU, and this addresses, let's say the list of addresses are like this, and we are looking for the page which are there in the main memory in the frames. Let's assume that the page size is 100 words. So we know that the virtual address or the physical address look like this. We have two part. One is the page number, another is the offset. The offset is depend upon what is the page size. So the page size, if it is 100 word, so what we can do is if this is means, let's say 437 is the uh, vir- virtual address or the physical address. So how we'll find out the value of p? Value of p will be find out, it will be divided by the page size, which is 100, and the value will become, will make it like this, and we'll take an integer value out of it. It will become 4. So 4 will be my page number. And when we do 437 and we'll do modulus 100, then we'll getting 37 is nothing but the value of d. So it is 4 and it is 3. So this 4 is a reference string. So here if we want to take the reference string of the page number, so how we'll make it divided by 0, and whatever the value will come in integer value, that will be my page number. So for that, the reference string will be, if the logical address or virtual address are given, so the reference string for page replacement algorithm is 4. This is again give me the 4, so no need to put another 4 here. This is again giving me 4, no need to put another 4. This is giving me 3. This is 4. This is 3. This is 1. This is 7. This is again 7, no need to write again. This is 8, because we are looking for the unique page referred. So unique page will be referred here like this. It is same pages, so we'll take it as a one, only one instance of it. This is 8, this is 9, and this is 7. then 6, 5 and 5. So we'll take 6 and 5. Another 5 we are not going to take. So this will as a taken as a reference string, right? So if the logical address is given, if the logical address is given. Now let's talk about different page replacement algorithm. We have three type of page replacement algorithm: first in, first out, optimal, and least recently used. These three are the popular page replacement algorithm. Let's see one by one. First, we'll see first in, first out. So, what is first in, first out? It is very simple page replacement policy. POLICY policy. New page will replace the older page. So, what will happen here is if we are getting in the new page, it will just pick up the oldest page and it will replace it. Okay. So these are the different page replacement policies. About the dirty page information and all those things we are not considering here, that we can consider when we actually doing the page replacement, because the page replacement has two perspective. Either that page will be swept in, swept out into the disk or not, or we just remove it from the main memory, because all the copy are there in the secondary memory, right? So whether we have to replace the secondary memory copy or not, it will be indicated by the dirty bit. If the dirty bit is 1, it means that some modification has been done into already done into the main memory. So we have to take that page into the secondary memory. Otherwise, we doesn't have to take it, because the operation related to the secondary memory, it is taking a lot of time, because the access time of the secondary memory is very large than the access time of the main memory, right? So let's assume that we have these reference string here. We doesn't have the logical address or the virtual address. Instead, that it is already given the reference string. This is reference string is reference to the page, and the frame size in the main memory is 3. So we have the frame size 3. Okay, so let's assume that I have 3 frames available into the main memory, into the main memory. And in the demand paging, we are using the pure demand paging. It means that initially all the frames are empty right now. Now let's fill it up. So in the first, we got the page fault, right? We got the page fault because if there is nothing, and if we require, so this is the sequence of the reference pages which is demanded by the CPU. So CPU first required 7. So 7 is not there, so I'll put 7. Then 0, 0 is not there, I'll put 0. 1 is not there, I'll put 1. So how many page fault occur here is 3. The next page fault I'll calculate later on. Now 701. Now the next one is 2. 2 is there? No, 2 is not there. So there is a page fault. So what we have to do? We have to replace, and we have to replace the oldest. So you see which is the oldest one here? 7 is the oldest one. So we'll replace 7 by 2. Then 0 will occur. 0 is there. There is a hit, right? Then 3 is occurring here, and which one we have to replace, which is the oldest one here? So you see the oldest one is 0, so we have to take 0 and we have to put 3. Now after putting 3, again it required 0, so which one we have to replace? We have to replace this, because this is the oldest one, and 0 will come. Then we required 4. 4 is not there. Oldest one is now 2. It will be 4. Now 2 The oldest is 3, so we'll take it, replace 3 and we'll put it 2. Here it required 3. We doesn't have 3, we'll replace the oldest one, which is 0. Again we need 0, we'll replace it. We need 3, 3 is there is a hit. 2, 2 is there is a hit. 1, 1 is not there, we have to replace the oldest one. Then 2, 2 is not there, we have to replace the oldest one. Then 0, 0 is there is a hit. 1 is there is a hit. 7, 7 is not there, we have to replace the oldest one. Then 0, 0 is not there, we have to replace the oldest one. And then 1, we have to replace the oldest one, right? So how many page fault occur? So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 12. And the total replacement, the total page fault occur is 5. 15, 15 page fault. How many hits are there? 1, 2, 3, 4, 5 hits. How many hits? 5 hits. So in the examination, it doesn't ask how many hits. It only asks how many page faults it occur. Now you can do the same thing with 4 number of frames. If the frame size equal to 4, then what will happen into the main memory and what is the page fault? So the page fault, when we take number of when we increase the number of frame, the page fault will also be decrease. So it will be 20. So generally what happened in the first in first out, when we increase the number of frames, definitely the page fault will be less. Why? Because the number of pages that will accommodate into the main memory will be more. So the page fault will be less, right? So uh, this the thing is, when we increase the page fault, it will reduce the, so the page fault, the frame size is inversely proportional to what? Page fault, right? So when we decrease it, page fault will increase. When we increase it, page fault will decrease. It generally happens. Now there are some sequence in which this problem, one problem is there in the first in first out. Let's see what is the problem. Let's assume that this is my uh, reference string, and this particular uh, reference string, uh, we are assuming like we have, let's say, number of frames as 3 initially. Okay, so let's see what happened. We are taking first in first out, we have the number of frame as 3. So let's say we doesn't have anything like pure demand paging. So this is 1, 2 and 3. So we have 3 page fault occur. Then we need 4. 4 will be replaced by 1. 1 is the oldest one which came, right? Which came first? 1 is came first. So 1 will go out. Then 1, 2, then 5. 1 is there is a hit. 2 is there is a hit. 3 required. 4 required. And 5 is there is a hit. So how many page fault occur? 1, 2, 3, 4, 5, 6. So total number of page faults are 9. Now let's assume that we are taking 4 number of frames. Let's solve the same thing with 4 number of frames. So we put the page like 1, 2, 3, and 4. Okay. Now 1 is there, 2 is there. Now 5 is not there. We'll take 5. So the previously 1, 2, 3, 4 will write. Otherwise, it will be a problem. So 5 we have to replace 1, and then 1 we have to replace 2, then 2 we have to replace 3, then 3 we have to replace 4, then 4 we have to replace 5, and then 5 we have to replace. So how many page fault? 1, 2, 3, 4, 5, 6. So this is 10. See what I told you in the previous, that when we increase the frame size, the page fault should decrease. But what is happening? When we increasing the page size as frame size, the page fault is also increasing. The number of page fault here is 9 and here is 10. That particular phenomena is called uh, Baladi anomalies. That is called Baladi's anomalies. What Baladi's anomalies is? Baladi's anomalies is the name given to the phenomena where increasing the number of page frame result in an increases in the number of page fault for a given memory access pattern, right? So when we increase the number of page frame, it is increasing the number of page fault, but that should not be there, right? It is the opposite which is happening. That phenomena is called Baladi's anomalies, right? Or Baladi anomaly. Let's go to the other replacement algorithm. The second one is called optimal page replacement algorithm. What it will do, it will replaces the page that will not be used for a longest period of time, right? That will not be used for a longest period of time. So that we have to replace. That is not going to use for longest period of time. So here what will happen is, so here what happen is we are looking for the future perspective. So that will not be used for longer period of time, right? So let's see and try to understand this particular page replacement policy. So first we'll go for the page number three number of pages. So let's see. Okay. So three number of pages. 7 is not there. We have to put 7. 0 is not there. 1 is not there, right? So 3 page fault occur. Now 2, right? So when we are in the 2, see here. So what we have to look for in the future? In the future we have to look. In the future we have to look in future and replace who is far. That's it. What we have to do, we have to look for the future and replace from here which is far. So how we'll do that? So we have to accommodate 2, but which has to be replaced, that we have to look. So you see 0 is used to, sorry, 017 is there. So 0 1, right? We got 0 and 1, we doesn't got 7 here. So 7 has to be replaced by 2. Then 0 is there is a hit. 1, so we doesn't have 3. So for that we have to look future, and 201 is there. So 0 is there, 2 is there, which is not there here in future. 1, so we have to replace 1 with 3. 0 hit 4. Now 4 is there. Look for the future. 2 is there, 3 is there, and 0. So 2 and 3 is there. 0 is afterwards. So we'll replace 0. 2 is there and 3 is there. There is a hit. Then 0. If 0 is there, 0 is not here, right? We have to replace some 2, 3, or 4. So which we have to replace 3 and 2. We got 4. We have to replace, right? So 4 will be replaced for 0. Now 3 hit, 2 hit. Now 1 is not there. We have to replace. Now look for the future. 2 is there, 0 is there, 2 is there, 0 is there, 3. So 3 will be replaced with 1. Then 2 is a hit, 0 is a hit, 1 is also a hit. Then 7, look for the future. Future is 0 and 1. 0 and 1, 2 will be replaced with 7. 0 is a hit and 1 is also a hit. So you see how many page fault occur. So 3 is occurring at very first. Then 1, 2, 3, 4, 5, 6. Total is 9. So 9 page fault occurs with these reference string and frame 4. What you have to do is you have to go for 4 number of frames and calculate the page fault. What is the page fault? So here you will get 8 number of page fault. Here we are getting 9, here you will get 8 number of page fault. Okay. So you can cross check here with this particular policy or this particular algorithm. Now let's go to the last page replacement algorithm, which is called least recently used. In the least recently used algorithm replaces the page that has not been used for the longest period of time. So we have to look for the older references or the historical references. Okay. Now it is this reference string is there. Frame size is also given. So I'll put the frame size here. 3 frame size are there. So we'll put 7, then 0, then 1 because all 3 are not there. So 3 page fault occur plus. Now 2, if we are 2, so we have to look for backward and we have to see what we have to look backward. We have to look in past and replace who is far. Previously what we have seen, we have to look for future and we have to see which is far, replace which is far. But here we have to look for the past and replace which is far. Now if we'll talk about 2, we have to put 2 here, but which has to be replaced? Look for the past. 1 is there, 0 is there, but 7 is very far, so we replace. Then 0, 0 is a hit, 3 we have to replace again. So 0 recently used, 2 recently used, 1 we have to replace with 3. Then 0, 0 is there, is a hit. 4 need to be, we have to replace anything. So 0 is there, 3 is there. So 2 has to be replaced with 4. Then 2, 2 is not there, right? So 4 we have just used, 0 and 3 has to be replaced with 2. Then 3, 2 and 4 we have used, then this will be replaced with 3. Then 0, 3 we have used, 2, 4 is the older one, so we'll replace with 0. Now 3, 0 is there, 3 is there, 2 has to be replaced with, okay, 3 is already there, right? So it is a hit. Now 2 is already there is a hit. Then 1 is not there, right? So 2 is there, 3 is there, 0 is very far, so we'll replace 0 with 1. Then 2 is there is a hit. 0, 0 is not there, 2 is used, 1 is used, 3 is very far, we'll replace it with 0. Then 1, 0 is there, 2 is there, 1 is also there is a hit. 7, 7 is not there, so I have to replace 1 and 0 is used, 2 we have to replace with 7. Then 0 and 1, this is 0 and this is 1, there is a hit and there is a hit. So how many page fault? 1, 2, 3, 4, 5, 6, 7, 8, 9. So total page fault are 12, right? Now when we increase the number of frames here as 4, so the page fault, you have to calculate the page fault, and this page fault is occurring as 8. So you look for that how many page faults are occur here, and then you can find it out.